Good morning to all of you all. In this video, we wish to see what is the basic definition of work. We know work is dot product of force and displacement, which is nothing but force, magnitude of force into magnitude of displacement into cosine of the angle between the force and the displacement. This formula is valid only when the force is constant. That is, the magnitude of the force should be constant and its direction should also be constant. If F varies in direction or magnitude or both, we need to define infinitesimal work for an infinitesimal displacement dr. So dw would be F dot dr, and we integrate work dw to get the total work as integral F dot dr. This is when F varies either in direction or in magnitude or both. We need to use this. You can easily see that this will reduce to this formula when F is constant. When F is constant, it can come out of the integral. So integral dr would be the total displacement. dr was the infinitesimal displacement. When you integrate dr, you will get the total displacement S. Now, let us take a very interesting example where we have a elevation like that. There is a pulley, there is a mass M here, and this string is being pulled by a person by a force F, and this mass, let us say, comes up by a distance L. Now, if you use this definition of work, F is a constant force. This force is constant. If you use this definition, the work would be the force into the displacement L. The angle between L and F is 90. So cosine 90. So we would say that the work is 0. But this is surely not the case, because we know when the person applies a force and pulls the string, this mass will rise up, there will be an increase in the potential energy, it will also gain kinetic energy. So obviously his muscular energy is getting transferred into kinetic energy and potential energy of the body. So obviously the work is not zero. So where is the fallacy in this formula? Yes, let us find that out. So we will once again go to the basic definition of work. Work is defined as the dot product of force and the displacement of the point of application of the force. Very important. Displacement of the point of application of the force. So that's very important. So let us say if this mass now goes up by L, this point of application will move by L. So the correct way to write the work now is force into L cosine of the angle between F and L, which is 0, into cos 0, and the work would be F into L. That is the correct way of seeing it. Yes, so let's not miss out this displacement of the point of application of work. For instance, if I had a rod suspended like that, I apply a constant force F to it. It is F like this. Then it comes like that. It is still, F is still like this. It's a constant force in magnitude and direction. We wish to find the length of the rod is L. We wish to find out what is the work done by this force. Okay. Now, the point of application of the force, this is the displacement. We can directly use this formula Fs cos theta because F is constant. Okay. So this is the displacement. So I will call this displacement vector as S. Now this is an isosceles right angle triangle. So this is 45. So the angle, this will also be 45, vertically opposite. So the work would be force into displacement of the point of application of force, which is S, which would be F into S into cos of 45. S cos 45 is nothing but the length L. S cos 45 is nothing but the length L. So S cos 45 is L. So this would simply be F into L. That would be the answer. That is the work done by the force. Now let us take an example from rotational mechanics. Supposing on a rough horizontal surface there is a disc which is rolling rather. There is a disc which is rolling. It's a rough surface, so there is frictional force. So how do we first understand rolling? We have already seen this in an earlier video. Supposing this is a rough surface and we have a disc here, it is rotating at omega and the center of mass is translating at V. So rolling, we know the combination of pure rotation about the center of mass and a translation of the center of mass. So that is rolling. Pure rotation and pure translation. Combination of pure rotation and pure translation is rolling. So let us say we have a situation like this. Friction is going to act at the point of contact. That is the frictional force F. Yes. Now the work done by friction would be the displacement of the point of contact. Force dot product of the frictional force and the displacement of the point of contact. Let us see how we can find the displacement of the point of contact. First of all, let us consider only the rotation. If you consider only the rotation, this point, let us say, let it move by a small angle d theta. Let the radius of the disc be r. So this r would be r d theta. Now since d theta is small, r d theta will be nearly straight. It will be straight. It won't be an arc because d theta is very small. So r d theta is the displacement towards the left of the point of contact. Now if you consider only translation, every part of the disc will have the same velocity v, and the point of contact also has a velocity v. So in a time dt, it will get displaced by v dt. Yes, this r dt is towards the left and v dt is towards the right. So what is the net displacement? The net displacement dr is going to be v dt minus r d theta. That is the net displacement dr. This dr we are assuming is towards the right. If v dt is greater than r d theta, dr will be towards the right. If v d theta is less than r dt, it will be towards the left. So we are assuming it towards the right, then the work dw would be f dot dr would be f into v dt minus r d theta into cosine of 0, let us say, because we are assuming this is v dt is greater than r d theta. So cosine 0. Well, if it so happens that this is greater, automatically there will be a minus sign which will come in and make the work as negative. This is the work. Now, where V d theta minus R d theta, V dt minus R d theta is the displacement of the point of application of the frictional force. Now what we need to do is integrate this to find the total work done by friction. For that, first of all, let us get everything in terms of time. Because we have got dt, we want the work done in a certain time, let us say t. So let us now see what is v dt. This v is going to vary. This v is because of the translation of the center of mass. So if you put this frictional force on the center of mass, that is treating the entire body as if it is concentrated at the center of mass and putting this frictional force on the center of mass, the acceleration would be F by the mass of the disk. So the instantaneous velocity V would be the initial velocity V naught plus the acceleration into time, where A is nothing but F by m into t. A is F by m into t. So we now have velocity in terms of t. So we can easily integrate it. Now let us see this r d theta. We know omega is d theta by dt. So this d theta can be put as omega dt. Now, if you see, this force is going to cause a torque in the anti-clockwise direction. So that torque will result in an angular acceleration alpha. So omega will change. So let us find alpha. How do we find alpha? Just as for force, we wrote acceleration is equal to net force by mass. The angular acceleration will be net torque. Net torque will be F into R. The torque of F about the center of mass will be F into R divided by the moment of inertia. That is alpha. So I can now write omega as if the initial angular velocity was omega naught. Omega will be equal to omega naught minus alpha t. Why do we say minus? Because alpha is in the anti-clockwise direction and omega is in the clockwise direction. So this would be omega. So what does the work become? The dW becomes F into V dt. V, instead of V we can substitute V naught plus F by m into t dt minus omega, and there is an R there is an R, and omega is omega naught minus alpha t dt. That would be the work. Instead of alpha, we can put this value Fr minus Fr by I t dt and simply integrate this. So the total work would be F into V naught dt, integral V naught dt will be V naught t, and this will be F by m t dt, integral will be t squared by 2, and here you would have minus omega naught r, integral dt will again be t, minus and minus becomes plus, so you will have f r squared by I and t squared by 2. So Roman's bracket here. That will be the work. Thank you.